In this tutorial, we will work through an example of how to find the rate law and rate constant from initial rates data. In this example, we will use realistic data for which the orders of the reaction are not perfect zeros, ones, or twos. We will solve for the exponents explicitly using logs. For the chemical reaction shown, use the initial rates data provided to determine the rate law and rate constant. The reaction is 2A plus B goes to C plus D. The table shows the initial concentrations of each reactant for the 3 experiments that were performed, as well as the experimentally measured initial rates for each experiment. As a reminder from lecture on how to use the method of initial rates, first you have to measure the initial rate of the reaction when the concentrations are known. Those are the 3 experiments above. Change the initial concentration of one of the reactants while holding everything else constant and measure the new rate of the reaction. Use this data to solve for X in a generic rate law by comparing the rates for 2 reactions. Repeat the process for each reactant. First, we need to find a pair of experiments for which one of the concentrations doesn't change. Let's start with experiments 1 and 2. In these experiments, the concentration of reactant B is constant at 0.2 molar, but the concentration of reactant A is increased by a factor of 3 from 0.01 molar to 0.03 molar. We can write a generic rate law for the reaction for each experiment using subscripts to denote which experiment we're talking about. Since we don't know the orders of the reactants, we use exponents X and Y to show the order of the reaction with respect to reactant A and B respectively. When we divide the rate law for experiment 1 by the rate law for experiment 2, we see that the K terms will drop out, as do the terms for the concentration of B, because these are constants. This leaves an expression in which the only unknown is the exponent X. To solve for an X in an exponent, you can take the log of both sides. By the rule of logs, exponents become coefficients when you take the log, so we have the following expression. Solving this expression for X gives a value of 0.145. Assuming that the true order for reactant A is a whole number, we would round this result to 0, and the reaction is determined to be 0 order with respect to reactant A. We can do the same thing using experiments 2 and 3 to determine the order of the reaction with respect to reactant B. Write the generic rate laws for experiments 2 and 3 and divide them to cancel out the K terms and the concentration of A terms. Plug in the values from the table, take the log of both sides, and isolate the variable y. In this case, after rounding the result to the nearest whole number, we find that the reaction is second order with respect to reactant B. The overall rate law for this reaction is then rate is equal to K times the concentration of B squared. Notice that the concentration of A dropped out because its order was 0. To find the value of K, substitute the data from any one experiment and solve for K. If you use experiment 1, the value of K turns out to be 1.3 inverse molar inverse seconds. Since there are 3 experiments, it's best to determine the K value for each one and then average the results. Our final K value is 1.4 inverse molar inverse seconds, and the final rate law is rate is equal to 1.4 inverse molar inverse seconds times the concentration of B squared.